In the previous lecture, we discussed about the quasi-static process. Quasi-static processes are the ideal concepts in which the system is always in a state of thermodynamic equilibrium or nearly in the state of thermodynamic equilibrium throughout a process. That is, when a system undergoes a change in state from one state to the another, then the system will pass through a series of thermodynamic equilibrium, so that in each step the system will be in a state nearly equal to or in a state of thermodynamic equilibrium. So now in this lecture we will discuss how to calculate the work done in a quasi-static process. To discuss the work done in a quasi-static process, consider a system contained in a cylinder which is fitted with a frictionless piston. Suppose the system is a gaseous system. So this is a system or a gaseous system contained in a cylinder which is fitted with a frictionless piston. Now consider that the system undergoes a change in its pressure and volume at a constant temperature. Now we know that the indicator diagrams are the diagrams which represents the variation of the any two of the thermodynamic variables. So here we will consider the PV diagram of this thermodynamic process, in which the pressure is taken along the y-axis and volume is along the x-axis. Now suppose initially the system is in the state A, and the system is changed to the state B quasi-statically from A to B. Now this can be represented by a curve like this. So the locus of this curve will represent different stages of thermodynamic equilibrium. So now to find the work done on the system or by the system to change its state from the thermodynamic equilibrium state represented by A to the state B is given by W is equal to integral dW, where this dW is the infinitesimal amount of work or small amount of the work done on the piston to move it through a small distance of dx at a pressure P. So this dW, the infinitesimal amount of work done, is from the mechanics we know that the work is equal to force into displacement. So F into dx is the work done by the system or done on the system. It depends on the condition to move its infinitesimal distance dx by the application of a force F. Now you know that the force is pressure into area, or we can define pressure P as force per unit area where F is the force applied on the piston and A is the area of cross section of this piston. Suppose we are considering this at a particular pressure P, let's say, then by applying at pressure P, by applying a force P into A, this piston is moved through an infinitesimal distance dx, then we can write dw as P into A into dx. But this quantity A into dx is the area of cross section, and the change in the position of the piston, that is dx, will actually represent the small volume dV. So this can be expressed like this, P into dV. So the total amount of work done, W, to change the state of the system from A to B is given by integral A to B dW, which is equal to integral P dV, and volume is changed from, suppose the volume at the point A is V1, the pressure is P1, so it is P1 V1, and it is, let it be P2 V2, then it will be P1, integral V1 to V2. So this expression, work done W is equal to integral V1 to V2, P dV represents the work done during a quasi-static process when the system changes from the state having the volume V1 to the volume V2. Now this one will actually represent the entire area, and if you evaluate this integral, you can see that this will be equal to the area under the curve AB, or we can say that if you take this point as C and this point as D, then it will be area under the curve A, B, C, D, A, or inside this area. So one thing which we have to note here is that if the work is done on the system, then definitely V1 is greater than V2. In that case, the work comes out to be negative, and if work is done by the system, usually V2 is greater than V1. In that case, the work comes out to be positive. So what we have to remember here is that the work done on a system is taken to be negative, and the work done by the system is taken to be positive. So this work is actually for a system when it undergoes a change in its state from the state represented by A to B in the indicator diagram. So this is actually a non-cyclic process. So this is the work done in a non-cyclic quasi-static process. Now we have to discuss what will be this work when the system undergoes a cyclic process. A cyclic process is a process in which the system, after undergoing a series of states different states or equilibrium states, and it returns back to the initial state. That means if you consider the indicator diagram for a cyclic process, you can see that the system comes back to its initial state after undergoing different processes, or after passing through different thermodynamic equilibrium stages. So, for consider the PV diagram, the volume is along the x-axis and the pressure is along the y-axis. Now, suppose the A is a state represented by a point having the volume pressure P1 and volume V1 in the indicator diagram. B is another state represented by the pressure P2 and volume V2 in the indicator diagram. Now, suppose when a force work is done on the system changes from the initial state A to the initial final state B through the path, let us call this path as through ACB. So, when a work W is done on the system, the system changes from A to B through the path C, so that we can represent like this ACB. In that case, the work is given by W1 is equal to integral along the path ACB dW, which is equal to integral ACB P into dV. Now, suppose the system now undergoes another series of stages of thermodynamic equilibrium and returns back to the initial state A through some other path represented by BDA. So, that is usually work is done by the system, and it returns back to initial state A from the final state B, that is B to A through another path D, that usually we represent it as BDA. Then in that case, the work done is given by W2 is equal to integral P dV with along the path BDA. Now, this W1 is actually represents the area under the curve ACB, and here this W2 represents the area under the curve BDA. Now, if you calculate the net work done on the system, W, which will be W1 minus W2, which is the area enclosed by the loop ACBDA. So, this is the work done in a cyclic quasi-static process. So, now we have to discuss work done in different processes like isothermal process, adiabatic process, isobaric process and isochoric process, that we will discuss in the next lecture. Thank you.